Weather forecasting has changed quite a bit over the years in terms of the accuracy of the forecast and indeed the methods we use to create a forecast as well. Now, historically, forecasts were made by using just one computer model, indicated here by this red line here. Let's assume this is the temperature forecast for the next 15 days for a given location. That would be your forecast, but of course, very rarely will that produce accurate results beyond a few days. And as you can see here, the dashed line, the observed values, starts to deviate quite a bit as you go forward in time, and particularly by the end of the run towards 2 weeks away, big differences in the forecast and the actual outcome. Now, by chance, there may be the odd occasion where they actually come close together, but more likely than not, that's purely coincidental rather than any particular skill in the model, for example. So we need to find better ways of improving our forecast in the longer range, and one of that is to do with the inputs into a model. A model is only as good as the data you put into it. Now that comes from observations, whether it's from ships and buoys over the sea or over land, radar and weather stations. And of course, twice a day, we also launch some weather balloons up into the air. That's the radio sonde here. Flying aircraft, they have lots of instruments on them to measure weather that's going on outside. And of course, above all that, satellite data, continuously monitoring the Earth and the weather throughout each and every day. All of this data then gets put into our computer models at the beginning so that we know what's going on and we can run that model forward in time to see what might happen in the future. But there are some limitations with this. For example, let's take a look at the weather stations across East Anglia. Each of these Stevenson screens is a weather station which is recording weather throughout each and every day. So we know at any one time what the temperature or the rainfall or the wind is like at any of these stations, which is good. But what we don't know is what's going on in between all of those stations, because it's not physically possible to measure these values in every single field and garden either in East Anglia or indeed elsewhere around the world. So we have to make some assumptions at the beginning of our forecast in order to run that model forward. And with assumptions comes a little bit of error. So the best way to do things is to use an ensemble, and by that we mean we take a guess, an educated guess using physics, as to all the possible different solutions we might have right now in a given field, for example. So we end up with 50 or more values, if you like, all slightly different, but only by a small amount, just to see what happens if we run that model multiple times. Will that have an impact on the forecast, or will the forecast stay the same regardless of these tiny changes at the beginning? That's how ensemble forecasting works effectively. You can see on this graph here for pressure, for example, lots of lines showing up. Each one is a different computer model, and at the beginning you would expect them to be very close together because there's pretty good agreement. The differences are very small. But with time, those differences start to get magnified, so the error starts to get a bit bigger, which is why we run multiple models to see all the possible solutions that the weather forecast models might produce going forward in time. So it's not going to give us necessarily a specific value for a given time in the future, but a range of possible values and which ones are most likely to occur based on where they cluster together. Now, clearly on this graph, there's a trend for pressure to build here for a time and then drop back down. After that, the signal becomes rather noisy, so we have to find some clever ways to pull out some of this data to make some meaningful decisions. Now, cast your mind back to the beast from the east back in late February, early March 2018. It was a significant spell, relatively short-lived, only lasted a week, but it saw disruptive snow across parts of the UK and actually the coldest March temperature on record as well. Now, the signal for this cold spell was there several weeks in advance. Now, this is that same graph using 50 different forecast members for Cambridge, for example. Each line is a different one of these ensemble members from our model. Very noisy, very hard to pick out any specific trends. This was from a forecast on the 5th of February. So to display it in a different way, to get some useful information out of all of this data, we can band some of these members together. The darkest shading through the middle here, that's the middle 50% of all of our members. So you can see that spans from 75% to 25%. Either side of that, we have other bands which account for smaller clustering of these ensemble members as well. Now, the key thing to point out on here, this red line, this is climatology. That's the normal conditions compared to average, if you like, at any given day at Cambridge, for example. So you can see this is for the minimum temperature. As you're going through late February into early March, that starts to come up slightly. Obviously, the sun's gaining more strength. Temperatures naturally get higher as you go into spring, which is why that curve is going up. The dashed line here, that's actually what happened on each night through that month of February into early March 2018. Now, the one thing you'll notice on here is actually about 2/3 of our Ensemble members fall below the red line. All of this blue shading is colder than normal, and most of it, 2/3 of it, is below that red line, indicating that signals were there 3 or 4 weeks in advance for a notable cold spell. This particular cold night carried a less than 5% chance of happening based on the data 3 to 4 weeks beforehand, but it still happened. Now fast forward 2 weeks with the newer run of our Ensemble members, and of course there's no data here because this is in the past as far as this forecast is concerned, but looking at the new data, notice how it's more clustered now below average. Most, if not all, of our members are suggesting a cold spell, and some are going for a significant cold spell as well. And you'll also notice this particular cold night, the percent chance has actually increased slightly as well. So this is how Ensemble data is useful for a site-specific location to point out the potential for disruptive cold weather. It's not going to tell you the magnitude until we get much closer to time, but it can tell you that a potentially disruptive spell of weather could be on the way. Another way to display it in map form, of course, is to take the mean of all of our members, all 50 members, averaged together. And this is what this map shows for the same period during late February, early March. And you can see much of Northern and Western Europe here in the blues, indicating below average temperatures. Again, it won't tell you necessarily the magnitude, but with a signal this strong 4 weeks in advance, given all the noise, that is quite significant. And finally, another way you can look at Ensemble data is to look at the percent chance of reaching or exceeding a certain threshold. So in the top graphic here, we've got the chance from all of our Ensemble members of being 5 degrees above average during this 3-day period, compared to the same value but below average, so -5 here, +5 on the top. And it's clear to see from these two graphics there was a much stronger signal for significant cold than there was for significant warmth. So as I stress, it's not going to give you exact values this far in advance, but it's very useful for highlighting periods of weather that could be risky to your business. That's the true power of Ensemble forecasting.